Hello everyone, let's start our discussion of Unit 4 with acids and bases with video 4.1.1. Okay, so we're going to start right off with an example so we can apply some formulas to this and learn them. So we're going to consider the solution of potassium hydroxide. So one, we're going to write all the formulas that are used to convert between the concentration of hydrogen ions, concentration of hydroxide, pH, and POH. So we're going to start with that. So I'm going to write all these formulas for you. Kw, and W stands for water, so this is the K of water, equals the concentration of hydrogen ions times the concentration of hydroxide ions. So just like we did in equilibrium, these are your products of water dissociating, and we'll go into that in a little bit more detail later, but these are the products here. And that's always going to be equal to 1.0 times 10 to the negative 14 at 25 degrees Celsius. So at 25 degrees Celsius, this number is always going to be true. Okay, so we have some other formulas here that are important to know. So pH plus POH is going to be equal to 14.0, and pH is the measure of acidity, or the number of hydrogen ions in a solution. POH is a measure of basicity, so alkalinity, and that has to do with the number of hydroxide ions in a concentration, and it only goes to 14, and this makes sense because the pH scale only goes up to 14. So the pH is actually also a measure of the negative log of the concentration of hydrogen ions. So this lowercase p here just means, excuse me, just means negative log. So lowercase p means negative log, and H stands for the concentration of H plus ions. POH then would be negative log, because we have that P, of the concentration of hydroxide anions. Alright, the concentration of hydrogen ions, we can actually go the other way using our log rules. It's going to be the inverse. It's going to be 10 to the negative pH. And don't forget this negative here, that counteracts this negative log there. And the concentration of hydroxide ions equals 10 to the negative POH. So you can convert from one of these. If you have one of them, you can convert to all of the other ones, and you can find everything. So if you have the concentration of hydrogen ions, you can find the pH. From the pH, you can find POH. From POH, you can find the concentration of hydroxide. You can get the K value, everything from just one of these values. Okay, so that was part A. Part B, estimate their values without using a calculator at 25 degrees Celsius. I'm going to switch colors just so we can keep this separate, because it's going to look kind of cramped here. So, estimating the values. So first I have a solution of potassium hydroxide. Now, just a side note really quick, make sure that you've memorized all of your strong acids and your strong bases. By this point, it's going to be really important that you're able to recall those very quickly. Okay, so potassium hydroxide is a strong base. And since it's a strong base, that means it dissociates 100% in solution. So that means it comes apart completely. So all of it breaks up into potassium ions and hydroxide anions there. So this is a strong base. So that means the concentration of potassium hydroxide that we originally have is going to be equal to the same, it's a 1-to-1 ratio, so it's going to be equal to the concentration of potassium and the concentration of hydroxide. So concentration of KOH equals the concentration of hydroxide ions and potassium, but we don't really care about that because when we're dealing with acids and bases, we really care about hydroxides and hydrogen ions. Okay, and that concentration was given to us up here. Now I'm just going to write this in scientific notation. So that's equal to 1.5 times 10 to the negative 4 molar. And that's the same here. It's the same thing, I just wrote it in scientific notation. Okay, how do we estimate? Because as you know, on the AP test, you cannot use a calculator on the multiple choice section. And a lot of the time they'll like to ask you what is the approximate pH of this. So estimating. So if we have 1.0 times 10 to the negative 4, that pH would be equal to 4. Because if you have 1.0 times 10 to the whatever, your pH is going to be equal to the exponent. So if we have 1.5 times 10 to the negative 4, we can say that that's between 1.0 times 10 to the negative 4 and 1.0 times 10 to the negative 3. So estimating, we have 1.0 times 10 to the negative 4 and 1.0 times 10 to the negative 3 would be pH 4 and 3. So our pOH actually is right between them. So 1.0 times 10 to the negative 4 is less than the concentration of hydroxide that we actually have, and that concentration is less than 1.0 times 10 to the negative 3. So that means that our hydroxide concentration here is right between these two, and so that means the pH is going to be somewhere between 3 and 4. So pOH, because we have hydroxide, is between 3 and 4. And if you actually plug this into the calculator, the pH is 3.82. So that estimation holds. So if the pOH is between 3 and 4, and pH plus pOH equals 14, that means our pH must be between 11 and 10. And in fact, our pH is 10.81. The hydrogen ion concentration is between 1.0 times 10 to the negative 10 and 1.0 times 10 to the negative 11 molar. And we know that because we have our hydroxide concentration between 1.0 times 10 to the negative 4 and 1.0 times 10 to the negative 3. We can only add up to 1.0 times 10 to the negative 14 total here. And so we know that 14 minus 3 would give us 11. And we know that 14 minus 4 would give us 10. And so that's how we're getting our numbers here. So that's just a quick way to go ahead and estimate when you're on the AP test and you can't plug these numbers into your calculator. Alright, I'm just going to switch back really quick to this other color, again so we don't confuse everything. So part C, determine whether the solution is acidic, basic, or neutral using these values. So this is basic, and we can tell because the pH here, let's see, what was our pH? Our pH is between 10 and 11, so the pH is greater than 7. So pH is greater than 7, pOH is less than 7, so pH and pOH, those are opposites. So if your pH is greater than 7 and your pOH is less than 7, you're going to be basic. Concentration of hydrogen ions is less than 1.0 times 10 to the negative 7 molar. So that's pH 7 right there. This would be neutral. If you had 1.0 times 10 to the negative 7 molar in hydrogen ions, that would be neutral. And 1.0 times 10 to the negative 7 hydroxide ions would also be neutral. But we have less than that. So since we have less hydrogen than that, it's going to be basic. And also, our concentration of hydroxide ions is pretty high. It's greater than 1.0 times 10 to the negative 7 molar. So it's much greater, in fact. So our hydroxide ion concentration is, let's see, 1.5 times 10 to the negative 4. It's much higher here. So since you have way more hydroxides than 1.0 times 10 to the negative 7, that's going to be basic. So what color is predicted for this solution with? So let's see if you can remember back to chemistry when you've done these experiments. When you put cabbage juice in a base, it turns green or blue. More like a greenish blue. Phenolphthalein, that was the stuff that we used at the beginning of the year in that penny demonstration in the big tank that turned it pink. Universal indicator would be a deep blue, purple color. You may not have seen this before. And litmus paper, the paper that's either red or blue that you dip in your solution to see whether something's an acid or a base. Litmus would either turn blue or stay blue if you used blue litmus paper. Okay, example 2. Solution A has a pH of 3 and solution B has a pH of 6. Each pH increment represents an increase of a factor of 10. Therefore, solution A has, well, if you have 3 factors of 10, it's going to be 1,000. So it has 1,000 times the H plus concentration. And as a rule, a smaller pH represents a greater concentration of hydrogen ions. Okay, example 3. Write a chemical equation for the dissociation or autoionization of water and the expression for the equilibrium constant Kw. So this word here, autoionization, auto meaning self, ionization meaning to break apart. So it's going to break apart itself. So that means H2O is going to break apart into H plus and OH minus. And very few, but always some, H2O molecules in any pure water solution actually exist at any given time as H plus and OH minus. Not very many, but some do. So let's go ahead and write what that chemical formula looks like. So the balanced equation would be 2 waters, and those autoionize, or they break apart, into H3O plus hydroxide. Okay, so this water is going to be liquid. H3O plus is aqueous, and hydroxide is aqueous. So what happens is one of the waters broke apart, and it gave its hydrogen ion to the other water. Now you can also write this as a net ionic, so you will also see this, or written as H2O liquid, just one of them, goes to H plus OH minus. This is more true of what the actual solution is. This is how it's written most of the time. You can write either one of these and you would be considered correct. So the Kw here, just like any K, or just like our Ks that we had before, those are going to be products over reactants. And here, remember, you only include aqueous, right, in your K expressions. We're not going to include liquids. So because we're not including liquids, there's no denominator. So it's just H plus times OH minus concentrations. So Kw, you might see it if you're using this equation written as the concentration of H3O plus times the concentration of hydroxide. Or if you're using just the net ionic, you can see it written as H plus times OH minus. And both of these are correct. Both of these are generally accepted. So you'll see these both everywhere. All right, if it's not stated, we assume a solution is at 25 degrees Celsius. So then Kw here is always going to be equal to 1.0 times 10 to the negative 14. So Kw equals 1.0 times 10 to the negative 14 at 25 degrees Celsius. However, at different temperatures, Kw changes. So at a higher temperature, at 100 degrees Celsius, the boiling point of water, Kw equals 5.13 times 10 to the negative 13. So it's a bit of a bigger number. From this, is the dissociation of water endothermic or exothermic? I want you to pause the video, think about it, and write down what you think and come back. Okay, so it turns out that this is endothermic. It takes energy. Endothermic. Because as the temperature is increasing here, it increased fourfold, Kw also increased. And that means when Kw is increasing, you're going to have more waters break apart, and they're going to turn into the ions. So your whole reaction is going to shift more to the right. And so because of that, because we create more products, we know that this is endothermic, because when you're putting energy in and creating more products, it's going to be endothermic. So as the temperature increases, Kw also increases. Meaning more hydrogen and hydroxide ions are formed. So overall, the reaction shifts to the right. What I mean by reaction shifts to the right is that the reaction is going to go to the right, it's going to create more products, or it shifts to the right. You'll hear all those terms. Okay, what are the pH, pOH, H plus concentration, and hydroxide concentration of a neutral solution, so that's pure water, at 100 degrees Celsius when Kw equals 5.13 times 10 to the negative 13. So remember, you have your different Kw here because you have a higher temperature. All right, so let's get to work. first we know that Kw is equal to the concentration of H plus times OH minus. That's the definition of Kw. And here we know that Kw is equal to 5.13 times 10 to the negative 13. Equal to 5.13 times 10 to the negative 13. Alright, so rewriting this, these are going to be equal to each other. So we can just call these both x. And I have two x's, so that's going to be x squared. So x squared equals 5.13 times 10 to the negative 13. So when you're solving for x, so x equals, x is the concentration of H plus, which is also equal to the concentration of hydroxide. And if you plug that into your calculator, you should get 7.16 times 10 to the negative 7 molar. So that's going to be your concentration of hydrogen, and that's going to be your concentration of hydroxide. Okay, so now what is our pH? So by definition, pH equals negative log of the concentration of OH, or H plus, sorry, let's do H plus first. H plus, and plugging in our numbers then, pH equals negative log of 7.16 times 10 to the negative 7. And if you plug that in, you get 6.15. So notice here now we have a neutral solution, but the temperature is higher. Normally we'd say, what's the pH of something neutral? And you would say 7. But here we've just calculated that our pH is 6.15. So if something is at 100 degrees Celsius and it has a pH of 6.15, that's the new neutral. So that means 6.16 would be basic, 6.14 would be acidic, 6.15, of course, is going to be neutral. So let's go ahead and find our POH. POH is negative log of the hydroxide concentration, which is equal to the pH, or POH is going to be equal to negative log, it's the same number, equals 6.15. So pH and POH here are going to be equal to each other, and that's the definition of something being neutral. So when you have pH that equals POH, they're the same molarity here, you know that that solution is neutral. So let's go ahead and figure out our, actually we figured everything out, I think. Yep, we figured out our pH, POH. Okay, and we figured out our H plus concentration. So at 100 degrees Celsius, the takeaway here, a solution with pH that is less than 6.15 is acidic. If pH is greater than 6.15, that is basic. Okay. Part D. What are the pH, POH, H plus concentration, and hydroxide ion concentration of that solution? This is the same solution we looked at earlier, but now we're at 100 degrees Celsius. Okay, so we're given already that this is KOH. From this, we can determine the concentration of hydrogen ions. So remember, this is a strong base. So the concentration of KOH equals the concentration of hydroxide, because these break apart in a 1-to-1 ratio, and this breaks apart completely. So we know that for every KOH, we're going to get one hydroxide. And so we know the hydroxide ion concentration already is this. So the hydroxide ion concentration equals 1.5 times 10 to the negative 4 molar. And that's just here. Scientific notation, 1, 2, 3, 4. Yes. Okay, POH, using our formula. Actually here, I'd like you to go ahead and pause the video and see if you can get the rest of the way. You're given the hydroxide ion concentration, get POH, then pH, and then the concentration of hydrogen ions. Go ahead. Okay, so coming back here, POH equals negative log of the hydroxide ion concentration So plugging that number in, we have negative log 1.5 times 10 to the negative 4, and that's going to be 3.82. That's your pOH. pH, well, up here we said that pH plus pOH equals 14, but now we're at 100 degrees Celsius, and we found over here that our pH is 6.15 and our pOH is 6.15. So we can no longer say that pH plus pOH equals 14, but we can say pH plus pOH equals 12.3. So you add these together, equals 12.3. So that's your pH plus pOH. So we can use this definition because we already figured it out at 100 degrees Celsius down here. So pH equals 12.3 minus 3.82, and that should give you 8.48. Okay, so that's your pH. From pH, we can figure out the concentration of hydrogen ions. So remember the formula for the concentration of hydrogen ions. That's equal to just 10 to the negative pH, which is equal to 10 to the negative 8.48, which when you plug in is 3.31 times 10 to the negative 9 molar. Alright, that's the end of video 4.1.1.